or wires you are dealing with. You have to vary the magnetic flux. You have here simply the representation of the three fundamental types of experiments of Faraday which show this in a wonderful way. In the first one, you have a solenoid linked to a battery, which is producing electric current when it's closed circuit. The solenoid generates a magnetic field. The magnetic field is conducted through the metal ring, or the metal core ring, okay, and enters a second solenoid, which has no electric current initially, and all of a sudden you observe an electric current. And you observe a variation, an augmentation, and then a decrease again. In order to maintain this induced current, you have to maintain the variation of the flux. And the second experiment is very simple. You take a magnet and you move through it, you move towards a given solenoid. See? And all of a sudden you will see an electric current through the solenoid. No battery, no nothing. Just moving a magnet. And the third one is even more impressive. You see a red, where's my British pointer? You have a red wire, a coil, no electricity in it, it's just standing there, in the magnetic field, and you rotate it, that's all. You do like this, you rotate, what do you see? Electricity. That's wonderful, huh? The principle of the dynamo mechanism. It just says that the essential thing which you have to vary is the flux of the magnetic field through a surface defined by the coils. This is the law. This is the law. I mean, this is the Faraday, Neumann, Lenz, and different names, law. It says that the electromotive force which is induced in the wires, in the coils, is proportional up to a sign to the variation of the magnetic field through a portion of surface in time. So what you should, if you want a lot of electricity, you should just increase not necessarily the value of the magnetic field, but the value of its variation, the speed of its variation in time, the velocity of variation. And you see, the final, I don't want to insist too much on this. You might have seen the Maxwell field equations in various experiments. You have the differential form, which I would call the differential form here, in terms of delta is like differentiation, okay? Just forget about the mathematical defeat. It's not difficult, it's very easy, but you have to get used to it, that's all. It's notation. This delta is differentiation. The cross differentiation is called a curl. It's a differential operator which mixes the component of the vector in a certain way. And this is the divergence. The del point is the divergence. This tells you, for instance, that the divergence of the electric field, remember the electric field created by a point charge, isolated point-like charge, is proportional to the density of the electric charge in space. This is Gauss's theorem. The flux, which is linked to the divergence, okay, the flux, which is linked to the density of flux lines through the surface, is related, I'll finish very shortly, don't worry, is related to the total charge, right, Q, in the end. And the four Maxwell field equations just express four fundamental experiments. Here you have Ampère and Oersted in one expression. A magnetic field produced by a current or a varying electric field. D here is linked to the electric field. I can explain to you if you want. This is the Faraday-Neumann Lenz law. An electric field is created by a varying magnetic field with a minus sign, remember? The sign. And this just says that the divergence of the magnetic field is zero. You remember that we mentioned that the flux lines of a magnetic field are closed curve. There's no divergence. Okay? There's no divergence. And here we are, these very non-mechanical, non-mechanistic equations, in the sense that you see what Einstein stresses on this, because Einstein started lots of his thinking by critically and deeply analyzing the Maxwell field equations. Here we have an object which is the electromagnetic field. You see, the electric field creates a magnetic field and vice versa. A varying magnetic field creates, in some sense, an electric field. So they are intertwined, almost unified. Right? And so you have an electromagnetic field, unification of these two things. The electromagnetic field, it's a field as well, which has its own structural equations. That's very non-Newtonian. The field itself has a dynamics. And one of the nicest, most beautiful manifestations of this intrinsic structure of the field itself is one of Maxwell's beautiful intuitions. Again, forget about the mathematics. If someone wants to see this, it's easy. I can explain it later or whatever. This just shows, you see, that the Maxwell field equations lead to equations which, in some circumstances, for instance, when there is no source, no charge or no current, you can have a wave equation. This yellow thing here is a wave equation. This is a second-order time derivative of the electric field, and this contains second-order space derivatives of the electric field. When you equal these both things, you can get wave solutions. And so Maxwell understands that his equations imply the existence of electromagnetic waves which travel and which exists in vacuum. Okay? And the speed, British pointer, the speed is linked to this value here. The product of epsilon and mu. Mu is the magnetic permeability of the medium you are in, a vacuum, if it's vacuum, and so forth. There's a similar coupled equation for the magnetic field. So I conclude just by saying this, okay, because this is one of the most extraordinary predictions. And here it is. It turns out that the speed with which these electromagnetic waves travel is the speed of light. And therefore Maxwell started thinking, well, light could well be an electromagnetic wave. A perturbation of an oscillatory perturbation or oscillation of the electromagnetic field propagating in vacuum, so it's totally immaterial, if you want. And this is coherent with the refraction phenomenon, because if you change medium, you change epsilon and mu. So you should change accordingly c, the speed of light, and this does happen in the correct way. So cool. This is another nice thing. This is a kind of conclusion. It just is telling you that all this electromagnetism, especially with its field, has a lot of peculiarities which are very non-Newtonian in character. If you're interested, they're all there. This is for spring, next spring. Because this is what led Einstein to relativity theory. There are problems in here. Conflicts between electromagnetism and Newtonian physics and Galilean physics. And this is the origin of Einstein's special relativity. Okay? I know I am always speaking a lot, so thank you very much for your attention.